Okay, good morning dear students. Today we can have a discussion about the electronic spectroscopy. Okay, first you have to look what is electronic spectroscopy. That is, that spectroscopy that is brought about by the interaction of any molecular system to UV and visible radiation, thereby inducing the electronic transition of the molecule from a lower level to the higher level. Okay, is called the electronic spectroscopy, otherwise called UV visible spectroscopy. Okay, that is the peculiarity of the spectroscopy. That is, it is brought about, the electronic transition in a molecule can be usually brought about by the action of or by the exposure of any molecular system to the UV and visible radiation. As you know, the UV and visible radiation is of wave number, UV and visible radiation, UV and visible radiation. Okay, there are wavelengths lambda ranging from 10 nanometer to about 800 nanometer, out of which 10 to 400 nanometer is the UV region, while 400 to 800 nanometer is the visible region. Out of which, out of the UV region, the UV region of interstellar, that is 200 to 400 nanometer UV region, is the near UV region, which are of interest in electronic spectroscopy. That is, if we irradiate any molecular system, or when we expose any molecular system to UV and visible radiation or the wavelength 200 to 800 nanometer, we can impart an energy equivalent to or affecting the transition of the molecule from lower electronic state to or ground electronic state to the higher electronic state, obeying quantum mechanical principle. Okay. As you know, the energy associated with the UV and visible radiation comes in the range of nearly 100 to 1000 joules per mole. Okay, the energy associated with the UV and visible radiation are all the order of, okay, that is the order of 100 to 1000 joules per mole approximately. Okay, 1000 kilojoule per mole. And the energy required for the molecular transition, or the transition of the molecule from the lower electronic state to the higher electronic state, the molecule is usually of the order of this, or the spacing between the two electronic states in a molecule, that is called delta E electronic, is of the order of 100 to 1000 kilojoule per mole. Okay, the spacing between the two electronic states in a molecule, or the energy difference between the two electronic state, the lower and higher electronic state, the molecule is of the order of delta E. Electronic is of the order of 100 to 1000 kilojoule per mole. The same amount of energy is carried by the UV and visible radiation. Okay, the UV radiation of the order of nearly, that is about 500 to 1000 kilojoule per mole they carry, and below 500 to up to 100 kilojoule per mole is carried by visible radiation. So generally, this much amount of energy is carried by the visible UV and visible radiation. So when expose any molecular system to UV and visible radiation for absorption, okay, they will cause, so they can induce the electronic transition within the molecule. So that spectroscopy is called UV visible spectroscopy, or other is called electronic spectroscopy. That's the general definition. So generally, again, that is the electronic transition that is induced or brought out in any molecule by the absorption of UV and visible radiation by exposing the molecular system to that radiation is called electronic spectroscopy, other is called UV visible spectroscopy. Okay. Then, next is, you have to remember another important fact in connection with the electronic spectroscopy we have to note is that is the energy difference. The delta E electronic is much greater than delta E vibrational, which is much greater than delta E rotational, that I already mentioned in the Born-Oppenheimer approximation. So when we carry out an electronic transition in any molecular system by the absorption of UV and visible radiation, it is implied that it is automatically accompanied by or simultaneously accompanied by the vibronic and rotational transition. That's an important thing or fact we have to remember. All the electronic transition are simultaneously accompanied by the vibronic and rotational transition. So the spectrum, electronic spectrum of any molecular system is a band representing the electronic transition. It's a band representing the electronic transition consisting of rotational fine structure and superimposed with the vibrational quiet structure. Here superimposed. So when we analyze the electronic spectrum of a molecule, the electronic, the band contained representing the electronic transition is superimposed with the rotational band, fine rotational line representing the rotational transition, and also that is quiet structure representing the vibrational transition. Therefore, the electronic spectrum of a molecule is a complex structure. It is always complex, especially in the case of a gaseous system. Especially in the case of a gaseous system within which the rotational degree of freedom are available. In the case of a solid and liquid system, the rotational fine structure are, since they are condensed system, the rotational degree of freedom is restricted. So we can see the electronic spectrum as a band consisting of vibrational quiet structure. Okay. But in the case of diatomic system, all the three can be seen in a spectroscopy or in a spectrum. That's the important thing. Then the theory behind, so as I mentioned, why we are using UV and visible radiation for electron transition. The answer is that the spacing between any two electronic transition in a molecule is almost equivalent to the energy carried by the UV and visible radiation, so they can cause or they can induce the electronic transition in a molecule. So that is our definition. The electronic spectroscopy or UV spectroscopy is that which it discusses, that deals with the transition of the electron from a molecular system from lower energy to higher energy level, followed by the absorption of UV and visible radiation. Then the theory. Okay. Then we have seen that according to Born-Oppenheimer approximation, as I mentioned, according to Born-Oppenheimer approximation, the total energy of any molecular system, the total energy of any molecular system is the sum of the three quantized energy. That is E total, the total energy of any molecular system, E total of any molecular system is equal to the sum of the three independent energies, according to Born-Oppenheimer approximation, that is E electronic plus E vibrational plus E rotational. Assuming that the three electronic states are independent, that is the concept of Born-Oppenheimer approximation. Born-Oppenheimer approximation. So for the Born-Oppenheimer approximation, we can take that, we assume that the total energy of any molecule is the sum of the three independent quantized energy, that is E electronics plus E vibrational plus E rotational, out of which I already mentioned E electronic is much greater than E vibrational is much greater than E rotational. Okay. So that means that any electronic transition is simultaneously accompanied by the vibrational and rotational transition. Suppose we are asking that E2 dash or E double prime is the total electronic state of a molecule, the initial state. Okay, this is the initial state or the ground state of the molecule, so that we can write E double prime total is equal to E double prime electronic plus E double prime vibronic plus E double prime E rotational. And let E single prime or E dash total be the final energy state, the final electronic state of the molecule. That is equal to E dash electronic plus E2 dash vibronic, E dash vibronic plus E dash rotational. So let us assume that E double dash represents the total energy of the system and E single dash represents, E double dash represents the total energy of the system initial state, and E single dash or E dash represents the total energy of the molecular system in the final state. The higher energy. Let E double dash represents the initial energy state of the molecule, and E dash represents the higher energy state of the molecule. Therefore, the spacing, the difference between the two energy states, the delta E total of the molecule is equal to E dash total minus E double dash total. And that is equal to, this minus is, that is E dash electronic, Okay, E dash electronic minus E2 dash electronic plus E dash vibrational minus E2 dash vibrational plus E dash rotational minus E2 dash rotational. So this become equal to, that is, so this is taken as, that is delta E total of the molecular system, that is spacing between the two energy levels, is delta E electronic plus delta E vibronic plus delta E rotational. Okay. This is the order of, as I have already mentioned, the total energy is sum of the total energy change of the molecule is equal to sum of the spacing between the electronic level, vibration level and the rotation level, that is the order of 100 to 1000 kilojoules per mole. Okay, this is about 10 to 100 kilojoules per mole, and this is about 0.0 to 1 to 1 kilojoule per mole. I have already mentioned. Suppose that when we expose a molecular system which is in the E2 dash level to a UV and visible radiation of energy H nu. Suppose we expose a molecular system to a UV and visible radiation. Suppose we expose a molecular system of initial energy E2 dash is exposed to a UV and visible radiation of, okay, such that by the absorption of energy from the UV and visible radiation, the absorption of energy from UV and visible radiation, the molecule is excited to from E2 dash to E dash level. E2 ആണ് initial level നിന്നും E dash എന്ന final level മാറി നമ്മൾ assume ചെയ്യുക. So that the energy that absorbed by the molecular system delta E is equal to, that is the radical amount of energy is absorbed by the molecular system from the radiation, that we can write H nu, that is equal to H into C into nu bar, now become equal to H nu is equal to H into C by lambda, that is H nu C bar is equal to delta E total. Okay, the amount of the energy absorbed by the molecule for electronic transition is delta Hc nu bar, now become equal to delta E total, that is equal to delta E electronic plus delta E vibrational plus delta E rotational. Therefore, the nu bar, the wave number of the radiation in terms of centimeter inverse to cause or induce the electronic transition is nu bar is equal to delta E electronic, okay, delta E total by H nu Hc, that is equal to delta E electronic plus delta E vibronic plus delta E rotational by Hc. So is the principle of it is the actual principle that shows the Bohr electronic transition or Bohr condition for spectral transition is by the absorption of the energy H nu from the UV and visible radiation, the molecule has undergone electronic transition. Okay, that is given by, that is the Bohr condition for the electron transition is given by the corresponding wave number of the radiation absorbed, nu bar is equal to delta E by Hc, that is equal to delta E electronic plus delta E vibrational plus delta E electronic rotation by Hc. Thus, that is so much centimeter. Thus, we have a rotational spectrum. Sorry, we have electronic band, electronic spectrum corresponding to this wave number, which is a complex structure, a electronic band containing rotational fine structure and superimposed with the vibrational coil structure as a complex structure is obtained. So that is a common structure. The picture of a rotational spectrum is that. Okay, if we plot the absorbance versus wavelength, we can like this. The type of that is, it consists of various lines. This is the type of the patient. It consists of rotational. This is a vibrational quiet structure, and this is a rotational line. This is the actual space. Okay, this is the manner. This is the type of the spectrum in the typical spectrum of electronic spectrum. Then next we are to the potential energy curve. Okay. The potential energy curve representing the electronic transition are usually called Morse curve. So, the electronic transition are usually represented pictorially by Morse curve. Okay, M-O-R, Morse curve. So called Morse curve എന്നാണ് നമ്മൾ represent ചെയ്യുന്നത്. Morse curve. Okay. That is a curve. A Morse curve is a curve that represents the variation, okay, the potential energy of the molecular system is plotted against the internuclear distance. This is the internuclear distance. Internuclear distance are as the x-axis, and the y-axis is the potential energy. So a Morse curve, or there is called a potential energy versus internuclear distance curve. A Morse curve is an ideal curve that represents the electronic transition, used for represent the electronic transition, which is a curve which consists in which the potential energy taken in the y-axis is plotted against the internuclear distance along the x-axis. For a ground state, the shape of the curve is like this. Okay, for a ground state, this is the state where R is the equilibrium, the middle point, the minimum point of the curve is represent the equilibrium internuclear distance. Any variation from the distance represent the extension of the oscillation or vibration of the molecule from the equilibrium distance. So this is the equilibrium internuclear distance. And the ground, this is the ground electronic level in which it consists of a large number of vibration states, that is nu. Okay. Number of vibration level, that is.